So let's look at the example from the slide. So calculate the stroke of a single cylinder pump if the cylinder diameter is 26 meters, blah 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 blah. So basically we have a Strada cylinder pump, and it has a piston right here, and it's discharging fluid out, then sucking fluid in, then discharging out. So we got, what do we know? We have a radius here, and the length of this is the stroke. We'll just call that L. So what do we know? We know that the volume of a cylinder is equal to the surface area of one side, so the area of a circle, times the height of the cylinder, which in this case is the stroke or length. So it's going to be pi r squared times L. So what does it give us? It gives us the volume flow rate. So the volume flow rate, so we know that there's 84 meters cubed per minute. Diameter is 26 centimeters. So then that means the radius is 13 centimeters. And let's try to keep everything in meters. So it's 0.13 meters. So we know this. We know that. And it gives us one other piece of information. So operating at 600 strokes per minute. So essentially we know that for every 1 minute, this is pushing, the piston is pushing from one side to the other, then back and forth, back and forth 600 times for every 1 minute. But that really doesn't help us if we don't really know the length or the stroke of this right here. Because I can give you something like this and just tell you, hey, this is going back and forth 600 times per minute. But if you don't have any dimensions, like if I don't tell you, hey, the length of this, so the stroke is, 50 meters, that's kind of exaggerated, or 10 centimeters, it kind of really matters, because this will mean essentially, you're pushing way more, fluid out for every 1 minute, whereas 10 centimeters, you're not really doing that. It's a lot less. So in this case, dimensions matter. We care about length of the stroke because that'll determine how much volume is pushing out. So strokes per minute really isn't enough because a volume flow rate is in meters cubed per minute. So on the other side, we had volume equal to pi r squared times L. So we know that, this is in units of meters cubed. Radius is meters squared. And this, let's just say it was in meters. The stroke or the length. And then the right side, meters squared times meters is meters cubed. So left side equals right side. Now, if we have, as we do here, meters cubed per minute, well then something on the other side has to be per minute. So either meters squared per minute for the radius, which that can't happen because we know the area is not changing. So then all that we can have is L per m, or meters per minute. We need to know how much meters is this really covering for every 1 minute. So for 60 seconds, how many meters does it cover? Well, we know that it goes back and forth 600 times. So if this was doing 1 stroke per minute, well then we would know, okay, if it's doing, from here to here, 1 stroke in 1 minute, then all we would have to do is multiply the length of this. Because let's just say this was 5 meters. So you're doing 1 stroke per minute. We did 1 stroke. Well, you would just multiply this by 5 meters per stroke. And unit wise it makes sense because strokes would cancel out and you would cover 5 meters per minute. Because you'd be going from here to here in 60 seconds. So same thing with this, 600. So you'd have 600 strokes per minute. Well, that doesn't tell you anything until we know how many meters are in one stroke. And that would be your L. Or you can call it H. Okay, so let's plug everything back into here. Or the volume flow rate. So we know that 84 meters cubed per minute is equal to, and then you know that the area of the circle doesn't change, so it's just pi times the radius squared. So let's just big bracket that off, times 600 strokes per minute times this big H, or L, or whatever you want to call it. So, you know, what do we want to do? We want to isolate H. We want to know how much that is. So we need H by itself on the right hand side. So we want to get rid of this whole, whatever this number leads up to, we want to get rid of it. We want to put it on that side. So we would do 84 divided by, and you can do it in steps or you can do it all in one shot. 84 divided by 600 times pi 0.13 squared is equal to H. So here we'll do it in steps. So H is equal to 84 divided by, so let's just pull out the calculator real quick. So pi is 3.14, we'll use that. 3.14 times 0.13 squared, 0.13 times 0.13 times 600, which gives us 31.84. Now it's just a simple case of dividing. So 84 divided by 31.84. So 2.6 0.63 meters. And you know, you can kind of check to see if this really makes sense, you know, because we can, every time you get a final answer, you can always plug it back in to whatever formula you had. So here, let me just do that in the corner. So, you know, on the left hand side we had 84 meters cubed per minute. That's our left side here. So now let's check if this right side was actually, or this whole right side was actually equal to 84 meters cubed per minute. We know that pi times 0.13 squared times 600 was 31.84. And what are the units? So we had pi, no units, meter squared. So meter squared, and then strokes per minute. And then we multiply that by, this is essentially 2.63 meters per strokes. So, you know, stroke cancels out. So it's meter squared times meter over minute. So it's meters cubed per minute. So the units are the exact same.